Welcome to today's explainer. So let's jump right in, because today we are looking at some AI news that is literally a game changer for one of the most frustrating bottlenecks in computer vision. Now, if you do any robust model fitting, whether you're writing software to help autonomous cars map 3D space, or just stitching a massive panorama on a phone, you know RANSAC is everywhere. It's the absolute workhorse running behind the scenes. But man, if you've worked with it directly, you know the misery of endless hyperparameter tuning. It's like chasing a constantly moving target. But what if you could just entirely eliminate that dependency? Well, today we're unpacking a newly proposed closed-form scoring method that completely removes the need for user-supplied inlier scale thresholds. We're going to dive into the theory, the math, and some seriously impressive benchmarks that could reshape how we handle robust model fitting. Here is our roadmap for the explainer today. We'll start with the RANSAC threshold problem, talk about breaking that circular dependency, dig into the closed-form math solution, check out the benchmarks, and wrap up with exactly how developers can upgrade.
All right, Section 1, the RANSAC threshold problem. Let's tackle the shared pain point we've all been dealing with for years.
So what is the actual issue with threshold dependency in the wild? Well, think about fixed residual thresholds. When standard RANSAC variants, and yeah, that includes upgraded methods like MSAC, SCA, and MAGSAC, when they try to score candidate models, they essentially have to draw a totally arbitrary line in the sand. They're counting inliers, summing up per-point scores, but they eventually saturate at a specific threshold that dictates what's a good data point and what's just noise. The massive flaw here, guessing where to actually draw that line. Every single one of these scoring functions demands a user-supplied parameter just to make that guess.
And here is the exact trap developers fall into. It's this nasty circular dependency. Your user parameter has to perfectly scale with the inlier noise distribution, right? But here's the catch. You have to estimate that parameter from the exact same contaminated data set that you're using to fit your model. Your threshold depends on the scale, but your scale depends on your threshold. When outliers mess up that initial estimate, everything degrades. And if your threshold is miscalibrated, baseline methods lose accuracy incredibly fast. We've all been there, spending hours perfectly tuning a pipeline, and then boom, a slight lighting change or a minor drop in camera quality breaks the whole shebang. For anyone doing two-view geometry or point cloud registration, it is just an endless cycle of manual tuning. Moving to Section 2, breaking the circular dependency. Let's see how we actually get out of this frustrating loop. To understand the fix, we kind of have to completely reverse how standard inference works. Old RANSAC relies totally on iterative scale estimation. You guess the noise scale, check it, tweak it, and score models against it in this endless loop. But this new method, it throws that iterative loop completely out the window. It mathematically marginalizes the inlier scale analytically in closed form. Basically, it shifts the entire problem away from guessing the scale, moving straight into direct partition optimization. It searches partitions directly, which means the inlier scale is just entirely absent from the scoring formula. You don't have to guess it because the math literally doesn't need it. Section 3, the closed-form math solution. Let's pop the hood and look at the actual analytical scoring making this possible. The real secret sauce here is the introduction of a conjugate inverse gamma prior. I know, that sounds super technical, but let's break down what it actually does. A conjugate prior is essentially an elegant mathematical trick. For a fixed inlier partition, the algorithm uses this prior to make sure the marginalization stays mathematically clean and solvable, tractable, instead of relying on messy guessing. By doing this, the final formula contains absolutely zero explicit inlier scale terms. It is brilliant. One single closed-form expression handles everything from the non-informative Jeffreys limit, where you assume basically nothing about your data, all the way to highly informative empirical Bayes priors. The equation just solves itself.
Because we have this beautiful closed-form solution, you don't need those heavy iterative refinement loops that usually tank RANSAC runtimes. Instead, you get this super elegant sort and sweep mechanism. Step 1, sort the residuals. Step 2, sweep through your candidate thresholds in one continuous pass. Step 3, compute the scores deterministically. You bypass all those massive pairwise distance calculations. If you think about it in big O notation, we're dropping from big O of n squared, which is all those heavy repeated threshold scans, down to just big O of n log n. For developers, that is literally the difference between your pipeline chugging for minutes versus finishing in milliseconds.
Section 4, benchmarks and unmatched efficiency. Let's talk about how this mathematical theory translates into real-world robustness. The researchers didn't just test this in a vacuum. They threw it at a massive, rigorous benchmark of nearly 70,000 image pairs. This wasn't some tiny curated sample. It spanned multiple two-view estimation problems, using both engineered and modern learned feature pipelines. They battle-tested the absolute life out of this to ensure it actually works in messy, real-world vision tasks. When standard RANSAC hits miscalibration, it suffers rapid degradation. It falls apart. Even the modern variants like MSAC and MagSac show moderate degradation if parameters aren't tuned just right. But this new closed-form method, its performance stays completely flat and incredibly stable. Across varying conditions, different noise levels, whatever you throw at it, the new score consistently crushes legacy variants simply by refusing to break when the inputs get messy. But here's the kicker, the really staggering efficiency gain. This new method hits near optimal accuracy using as few as 2 validation pairs. 2! To get that exact same level of performance, standard methods need about 100 times more validation data. Think about what that means for a minute. That's a huge reduction in compute time, way less data wrangling, and a massive cut to your server costs just to validate models. And it's smart, too. As your validation data shrinks, the algorithm automatically tightens its prior regularization. It seamlessly shifts between data-rich and data-sparse regimes on the fly. It finally does the heavy lifting so you don't have to babysit the parameters. Plus, because the scoring process runs in big O of n log n time, the overhead is phenomenally low. It is perfectly suited for real-time geometry estimation in super fast-moving environments. Think robotics or autonomous drones.
Finally, Section 5, how developers can upgrade. Let's talk actionable implementation steps for your own projects.
If your pipeline uses RANSAC for camera pose estimation, structure fitting, or point clouds, upgrading is shockingly straightforward. You don't have to rewrite your whole sampling loop. Just swap out that old threshold-based scoring function for the new closed-form marginalization. Keep your existing partition optimization and just let the sort and sweep routine handle the ranking. But a quick pro tip here, absolutely pin your feature extraction pipeline versions before you swap scores, because learned extractors can shift your residual distributions. And if you're writing this in C++ or Python, verify your sort and sweep actually runs in big O of n log n time, otherwise you're throwing away your speed gains. Run a regression test, track your inlier ratios, and you'll likely see the same or better accuracy without ever manually tuning a threshold again.
Which brings us to this final thought. By eliminating the circular dependency, slashing the needed validation data by 100x, and offering a rock-solid closed-form math solution, will threshold the scoring just become the new industry default? Honestly, it feels like the days of endless parameter tuning might finally be over for good. Thanks for tuning into this explainer and keep building.